Hello, everybody, and welcome back. In my experience as an engineer, as well as working in marketing and sales and operations and management, life has plenty of problems. And the way that you make a name for yourself, the way that you earn money in the world, the way that you really make a difference is by solving other people's problems. But that being said, word problems, however prevalent and however valuable they are for us to learn how to solve, can be quite challenging. So today we're going to kind of walk through and build a lot of our comfort with them, and we're going to talk through some strategies that I've found really help me whenever I feel like I'm getting overwhelmed by a problem, and I hope they're going to help you out as well. So the first thing that I would absolutely recommend is that we always start off by just taking a deep breath. A lot of times it's going to feel like we have a problem that is catching us by surprise, that we don't know what to do, that there's just so much going on that we weren't prepared for it, and this is perfectly natural. In fact, this is maybe one of the best things to practice in math class in preparation for a future job, is that we're going to be thrown into situations that we're just unprepared for. I can't tell you how many times I've been asked to go fix a problem that I didn't even create, or how many times I was hired to do a job that I had never studied for. In fact, in one of the first jobs I ever had, I was brought on to do some manufacturing engineering work. I was put in an assembly line where they would take copper plated objects and they would try to put silver on top of them. They would use a thing that was called electroplating. So you would dip a piece of copper into a bath that had a whole bunch of silver in it. You'd put up some electric charges to it, and it would attract the silver and latch it on securely to the copper. So you would get this beautiful kind of proofing that would happen at the bottom of these objects. Well, about a month into my position, the entire assembly line stopped working. For some reason, the silver wouldn't stick anymore. It wouldn't bond. And the person who had invented this process had long since retired. There wasn't a lot of documentation lying around for how to make these things repair. The number of different things we had to try was astounding. You had to change voltages and how long you kept things in the water and how much silver you put in the water. And I was the only one, and I had never studied how to do electroplating. I had never studied how to, be a chemical engineer, but you're the only person for the job. You're the only one there. That's why you were hired. And so you have a choice. Either you solve the problem or the problem doesn't get solved. So what do? You take a deep breath and you try something. So that's kind of my second suggestion. Is we've got the first thing, we're going to take a deep breath. We're going to acknowledge that we feel overwhelmed, but we're going to start somewhere, whether that's drawing a picture, whether that's trying to go and ask certain questions of ourselves, or back into the word problem. We're going to do something that gives us a place to begin. After all, Rome wasn't built in a day. If you're asked to eat an elephant, you're going to do that one bite at a time. Insert your favorite cliche here, and you're not going to solve problems if we don't start the problems first. So we're going to put something down that makes a little bit of sense to us and start getting our eyes involved. And in fact, that's actually my third suggestion. My third suggestion is to try to draw a picture, sometimes a graph if we really have the ability to make things mathematical, but we want to try getting our eyes involved. About 80% of the information that we process as humans comes through our eyes. For those of us who have vision, like that is how we do most of our thinking on a daily basis. So we want to try to put as much down on the paper in front of us as possible, really give our intuition something to latch onto. But that being said, we can't of course draw the entire situation. We are not artists, so we will have to do a little bit of summarizing, find the important things to put down. So that's my fifth suggestion for you, is make sure that if you are trying to take a large problem and solve it, bring out just the things that you think are important. Ask yourself, if you were going to be describing this problem to a friend of yours, what would you tell them about the problem? You probably wouldn't recite it from memory. You'd probably say like, hey, I've got this really difficult word problem. There's, this cow and this guy named Farmer Brown, and we're going to try to latch it, and tether it down someplace. I think that's going to get us a circle. Like, we're going to try to do it very lightly with just enough to get the story across. And that's going to be a great way for us to take a large problem and to make it much more approachable. Another suggestion of mine, let's make sure that we are giving things meaningful names. After all, we see X's and Y's all over the place in our math equations, but maybe if we're working with something like how long is the lead that I should tie on Farmer Brown's cow, maybe I would call that L for long or length, maybe L for lead, and I would call it L in my problems instead of X. That way I have less to remember. Every time I see L, I'm going to naturally think length or something that starts with L, versus if I put down the letter X, maybe I have to remember exactly what I'm thinking about and solving for and what was my question to begin with. Let's give ourselves a lot of kind of intuition here. And then the last thing I'm going to suggest is just let's try making sure that we're being creative, that we're being open problem solvers, that we're looking at many different perspectives we can approach the problem with, and that we're not trying to solve these things from what do I need to do, but just what's something that I could do, what's something that does make sense to me, what's something that I could begin with, and then adjust from there. So to make all of this anchored in, we're going to work through a number of different problems today that are going to feel nice and intuitive, hopefully. And from there, we'll build up this intuition, this process, and grab at these tools that we already have in our tool belt as we feel like we need them. So I think an important place for us to start is to remember that we've been dealing with word problems any single time that you've ever described a problem to a classmate or a teacher or yourself in class. These are all word problems. We speak in the language of words and not in symbols. So when we're working with some of these problems that can appear intimidating, it's important to think, well, maybe this isn't about trying to go into the storyline. Maybe it's just like we're trying to understand a friend and help them understand the math that they're describing. So in this situation, let's deal with something that hopefully should feel nice and elementary, something that's a nice warm up again. So let's imagine here you've got some sealed containers that they've been delivered, and I've chosen to say that these are going to be sealed containers filled with frogs. But I mean, if you feel like this needs to be a little bit more applicable to your eventual career, then think about these as being medical containers, or think of these as being foodstuffs, or think of these as being anything that you're eventually going to have delivered to you, or that's maybe going to be something you use in your job. But I think frogs are a little bit more fun, so we're going to start with those. So let's imagine that we've got these crates of frogs. Some of them have been able to escape out of the crate after shipment. Some of them are still contained in there. We don't want to open these crates. If we do, the frogs will get out. And again, like this feels like a kind of silly example, but for medical stuff, this happens all the time. You can't just open containers and measure it. You've got to find a way to work with things without getting at the substances themselves. So here's the thing that we've been able to figure out, because we want to figure out how much are in these boxes. As it turns out, they're not labeled, so we can't just read it off. Oh, what a bummer. But we have been able to kind of be a little bit creative and find out that if we put them on our scale and we balance them in just this certain way, we can find out that we have the same amount of stuff on the left as we have on the right. So take a look here. So we've got these crates, as it looks, we've got 3 frogs and 2 crates on the left-hand side. I've been able to balance with 5 frogs and one of the crates on the right-hand side. And we found that this is going to be something that's well balanced. So how would we express this if we were thinking of it in terms of a math equation? Well, we could say I've got 3 frogs, 1, 2, 3 of these frogs over here. We could say, okay, well, that would be no problem. I would have a frog, at the very least, a frog, another frog, and then 2 unknowns crates. Let's maybe call those X's. So we'll have another crate and another crate over here. And that's going to be the same thing as having 1, 2, 3, 4, 5 of these frogs. So frog, 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 and frog. And then a crate over on the right-hand side. Now, this is a great way to kind of start and express things off as you would for an equation. But maybe I don't want to think of it in terms of an equation. Maybe I want to just talk about how I can build this intuition with doing some pictures. Let's put this off to the side and come back to it. So what's the first thing we could do if we were just trying to simplify up this scale? Well, the very first thing we could do is just maybe take some things off of both sides. So let's sketch this entire scale again. We'll put on the left-hand side and the right-hand side. Maybe we notice that I have 1, 2, 3 frogs over here and 1, 2, 3 frogs over here, that if I take them both off, I should have the same things on both sides. So let's maybe do that. Over on the left-hand side, I'll take off 3 frogs. I'll take off a frog, and another frog. And left on the scale now, we have our 2 unknown crates. And over on the right-hand side, if I take off my 3 frogs, frog, frog, and frog, I have 2 frogs that are left over and an unknown crate. Well, okay, from there, what could we do? We could absolutely just take off one of these crates as well. And so we could say maybe over here, I'll take off a crate and I'll just go back in and kind of erase this. And similarly on the right-hand side, we could just kind of take off a crate. We're going to keep the scale balanced. And so how much do we have in each crate? Well, if all I have left is one of these crates, then it's essentially saying that I've got one of these unknown boxes, and on the right-hand side, I've got some of these frogs. Let's see how well I can kind of draw these frogs. I don't think that looks too bad. There's a frog and there's a frog. So how much is going to be in each crate? It's got to be 2 frogs, because that's exactly what we have balanced on both sides. Now, we've seen this when we've been working through in equations. After all, we could look at this as just simply saying I'm subtracting things, I'm subtracting the frogs away, I'm subtracting the x's away, but I want to suggest and propose that we maybe look at this a little bit more technically in preparation for what I'm going to get to in a second. Maybe instead of just writing this idea of saying I'm taking away 3 frogs from both sides, and I kind of write this as just underneath the things I'm taking away. Not that this is wrong, but I just want to propose a different perspective. Maybe what I'm really doing is saying that at every single time I am taking away something that is equivalent, something that's an equation, something that's a statement that has to be true. So here's the way that I'm going to kind of look at it. What if, instead of just subtracting these frogs, I say, on the left-hand side, I am going to have 3 frogs. On the right-hand side, I'm going to have 3 frogs. They are the same thing, and I'm going to take it all away. Now that's a little bit of a different way of kind of writing it, but I hope that this feels like it's not too different. I mean, after all we're doing is kind of subtracting equations, and in that, what we're saying is we're subtracting things that are equal. Okay, well, what's that get us? If I take away things that are equal on both sides, then I should get a new equal statement, and I should be left with saying, okay, I have x plus x left over here, and on the right-hand side, we would have, let's see, 2f's plus an x. And we could take away things so long as they are equivalent. We could take away a new equation, something that we know is equal, something that we know is the same. So here I could take away x equal x from both sides, and sure enough, that would get me x equals f plus f. So what does that mean? X has to be equal to 2 of my frogs. And that's an okay place for us to begin with. In each box, I have 2 of these frogs. So this is a little bit of a different idea, this idea of kind of taking away from both sides being equations, but really I'm hoping that we'll recognize that what we were doing all the time when we were just writing minus f below stuff is that we were doing this. We were just doing this in a shorthanded way. We were saying that if I just subtract something from the left-hand side, I have to subtract it from the right-hand side? No, that's a rule. We're saying the only way to even make sense to take something away from one side is if I take it away from the other, because the only way that I can adjust something that I know is true, that I can make it look different, is that if I change both sides in a way that is also true. We'll see in a couple examples of why this is really, really useful. Because let's take a look now at the second problem. So let's imagine that we're at a theater. There's a little bit of a more real world, hopefully applicable problem. So we're at the theater. 2 of your friends pick up sodas and popcorn while the rest of you went to go get your seats. One friend got 3 popcorns and 2 sodas and paid $23.75. Another got 2 popcorns and 1 soda for $14.75. Okay, that's a lot of information. No one is caring at the theater what that all happens. But on the way home, you're trying to decide how much you need to pay back one of your friends because you drank one of the sodas. And this theater was a simple theater with something that didn't give you an itemized receipt. We can't just look and pull it off. How do you know how much to give your friend? Well, this seems a little bit more applicable. We've gone to the theater, we've had a couple friends treat us, but we'd like to pay them back. How do we do that? Well, on the car ride home, maybe we're not thinking of all of the different math skills we have, but maybe we remember some of the basics. We could absolutely just draw a picture, try to sketch this entire thing out. So let's take a look at what we have on each of the receipts. On one receipt, we had 3 popcorns and 2 sodas and this amount of money that was paid. Well, let's just draw that out. I'm going to make my popcorns be boxes, like little boxes of popcorn. So I have 3 boxes of popcorn, and then I have 2 sodas. So maybe those would be, I don't know, I could draw them kind of sideways with a straw picking out. So there we go. So I've got 2 sodas. There we are. And then for the other, you've got 2 popcorns and 1 soda. Okay, because this one was $23.75. And then the other one, once again, we had 2 popcorns and 1 soda. For $14.75. And so maybe we're looking at this and we're trying to figure it out, and what do we see? Well, we can maybe look at trying to just find the difference in between them. I mean, maybe after looking at these pictures, we start to recognize that really what we have is just 1 more box of popcorn and 1 more soda on the first receipt. Okay, well then shouldn't that kind of make us think that the difference between these 2 things, that 1 extra box and popcorn and that 1 extra soda should be whatever the difference is in between these 2? And we could kind of calculate that out, but maybe we start to use what we had above. Maybe what we're really looking at is just saying we're taking away this entire statement from the one above it. After all, if we have 3 popcorns and we've taken away 2 of the popcorns, that leaves us with a popcorn. 2 sodas taking away a soda leaves us with a soda. And $23.75 taking away $14.75 leaves us with $9. So maybe we haven't gotten exactly to an answer yet, but we certainly have used 2 things that were true to find something else that was true. Okay, so we could absolutely do it like this. I'll keep it as pictures and then we'll go back and adjust it with some symbology in a moment. But then maybe I'm looking at these 3 statements that are true and I'm trying to figure out, okay, well, what do I have to just find out how much I have in that one box or that one soda? We'll take a look at this ripple effect. I now have 1 box of popcorn in my third statement, and in the second statement I have 2 boxes of popcorn and they have the same amount of sodas. Maybe I could think of subtracting that whole statement away, or in other words, just recognizing that what's the difference between my third line and my second line? There's 1 more box of popcorn on the second line, so that must account for the difference that you have here, $5.75. So we're just kind of rippling through and saying, okay, well, what's the way that I can kind of deduce or I can logic through how much I have difference between each of these statements? Well, sure enough, now I can even look at this last statement and say, what's the difference between this box of popcorn equaling $5.75 and saying that if I put on a soda, it's $9 in total? Well, I can just kind of subtract that and say that I'm looking for the difference here. And sure enough, that's going to have to be whatever the difference is between $9 and $5.75, which I think is 3 1/4. And so we're able to get to an entire solution by just simply saying, okay, sure enough, let's just take these statements that are true and keep looking at their differences. Let's subtract this one over to find out what we have at the bottom. Then I can say, I'm going to take the next one here and just subtract it to find out the next line of conclusion I could figure out from here. I could just subtract this one here. And then from here, I was able to kind of do the exact same thing and ripple that one on down. I could look at it and saying, okay, well, what if I just did this one above this third line minus the second line? And that got us to a nice solution. I need to pay back $3.25. Okay, so the pictures absolutely work as a fallback. What's a way that I could write this in some symbology, a way that we can track our work and explain it to somebody who isn't just watching us sketch away on the back of a receipt? Well, let's put that into the space on the side here. So over here on the right-hand side, maybe we decide that instead of calling these things boxes of popcorn and drawing actual boxes and taking the time to draw out these sodas, well, maybe we can just use some variables. We'll give these things meaningful names. So let's start with saying, okay, maybe instead of saying 3 boxes, I'll just say I have 3 of these popcorns, and I'll write that off, recognizing that if having 3 of something is just multiplying something by 3. And what do we also have over here? We have 2 of these sodas. So I could say I have 2 sodas, and that in total, that's going to get me $23, excuse me, and 75 cents. So there we go, $23.75. Well, as we kind of saw in our picture, we had another receipt which said that I had 2 of these popcorns and a soda, and that was going to be $14.75. Well, what did we do in the first situation? We kind of did some subtraction here, right? So maybe I like to label this off and say, since I'm about to do a lot of rippling, I'll call this equation 1 and I'll call this one equation 2. And I could say what I'm about to do is take away equation 2 from equation 1. And I'll make myself a little bit of a note. 1 minus equation 2. And if we do that entire thing, that's just going to be, subtracting that on down, would be, let's see, 3p minus 2p would be 1p. And 2s minus s would be an s, and then $23.75 minus $14.75 gets me my $9. And I could call this equation 3, right? So if I was going to use this one again, so I could say maybe something like, I'll be a little bit, I'll move this over and I'll say I have equation 1 minus equation 2 gets me equation 3. And these are all just as equal and valid of truth statements as each other. So now I can kind of watch myself work as I'm moving through this entire thing. Because after all, in this next line down here, what was it that we were really kind of recognizing is that I have 2 popcorns and a soda got me $14.75, but 1 popcorn and a soda was $9. Well, then I can just say, okay, well, let's do equation 2 minus equation 3. So maybe I need to write this one out a little bit more clearly. This would be 2p plus s equals $14.75. and I'm going to take away the popcorn plus soda statement at $9. And that was going to get us that I have 1 popcorn left over, no sodas, and $5.75. Okay, well there you have it. That's going to be my 4th equation right here. And then what were we using to try to, well, we were trying to find 1 soda, so I can look back through all of my statements and I could say, okay, maybe I have, oh, this one right here, equation 3 again, has 1 popcorn and 1 soda. So let's write that one. That would be, I would do equation 3 minus equation 4, and that would be the same thing as saying popcorn plus soda is equal to $9. And if I take away popcorn at $5.75, oh, try not to run out of room, we're going to end up getting that, sure enough, that's going to leave us with $3.75, or $3, excuse me, and 25 cents, the exact same thing we have right here for an answer. Okay? So there's a lot going on in here. We're going to, now that we've kind of explored the intuition, on the next couple problems, we're going to find ways to organize this better because I think it got a little bit cramped. But I want you to see this idea of just simply saying that I can subtract equations from each other. It's nothing different than what we've played with already. We've been doing that every single time we've done the same thing to both sides, and we've done it when we've been talking here about just looking at how the pictures kind of ripple into each other and what's left over after I make a few different statements. So how can we organize this with something that's a little bit more broad? Well, let's take a look at this one here. So how many gallons of 50% salt solution and how many gallons of 10% salt solution would have to be combined to make 4 gallons of 20% salt solution? Woo, okay, solutions, percentages, gallons, word problems, that's a lot. Deep breath time, okay. How would I do this as a picture? I'm gonna go back to thinking maybe we do this as a picture. How many gallons of 50% salt solution and how many gallons of 10% salt solution would have to be combined to make 4 gallons of 20% salt solution? Okay, that seems like something that we would do in a lab. I'm kind of thinking like maybe beakers and equations all mixing around and how I would maybe do something in my kitchen. Maybe that's an idea. Maybe we'll start off with just kind of drawing these things as if I was kind of sketching them out as a container. Let's do 50% of salt solution. So how many gallons of 50% salt solution? That would be, I take a bucket, I put a bunch of water in it, and half of that water is salt. Okay, that seems like a good picture. That captures the idea of 50% salt solution pretty well. What's 10% salt solution going to be? That's going to be a different bucket that I could make where I have water in it, and maybe I do 10% of this is salt. And so that would be what, 10% right here? I'll put something in my picture, and 50% right here. Okay, so far so good. And then I'm eventually going to try to mix and match these things. So we've got some kind of process here I'm not quite aware of, but I'm eventually going to get 4 gallons of 20% salt solution. Okay, so that's going to be 4 gallons, 1, 2, 3, and 4. Each has 20% salt solution. So here we have 20, 20, 20, and 20 of salt right there. Okay. That seems much more reasonable. How would we actually go about doing this? Well, I'm definitely feeling the need or the desire to pull out some kind of equation, something I can manipulate a little bit more easily than these pictures here. Well, I also would like to maybe consider something like we had above, where I have like the 2 receipts idea, or essentially 2 statements that I could play off each other that I could kind of bounce around. What are some different things that we actually have going on here? Well, the first thing that I'm kind of thinking about is that we have a certain amount of the 4 gallons that we have to create over here. I mean, after all, we've got 4 gallons. Maybe that's an important thing. I'll write the amount of volume I have over here. So my final volume has to be 4 gallons. How much salt do I need to have? 20% salt? How much is that? That's 20% of my 4 gallons. Oh, okay, so there's 2 things actually hidden in here. One says I need to have an amount of gallons, and the other thing that says I have to have an amount of salt. Well, let's explore into that one. Okay, I think we've got maybe a place that we can begin. Let's first talk about our gallons. How many gallons do I have? I've got 4 gallons, sure enough. And I got those gallons by combining some of this 50% with some of this 20%. So maybe I need to think of some ways to label this one over here. Let's call this one solution X, and let's call this one solution Y. I don't really have any better names, but I know that I'm going to have a certain amount of my X and a certain amount of Y that's going to have to combine together to get me my 4. So here we go. However much I have in my first situation and how much I have of my second solution is going to combine to get me 4. And to keep everything straight, we'll label this off to the side. X would be the number of gallons of 50% solution. And the Y is going to be the number of gallons of 10% solution. And if I combine those together, I will get 4 gallons. That's what the word problem says. Okay, so that works out just fine. But I also need to make sure I'm accounting for the salt. Let's think about how the salt would work out. So what do we have for the salt? Well, I know that I'm putting a certain amount of salt into all of this over here. Would be, let's think, how much salt do I have in this statement over here? I have 20% across 4 gallons. So I'm gonna have to end up with 20% across 4 gallons. 20% of the 4 gallons would tell me how much salt I have over there. Okay, on the left-hand side, what are we talking about? Well, how much salt do I have from the 50% solution? That's going to be, well, I guess 50% of however many gallons of the X that I'm putting in there. And I'm going to be combining that with 10% of however much of the Y solution I'm putting in there. Okay, so it's hidden, and I'm not necessarily saying that this is a problem that we would see the solution to right away, but I think that this is kind of cool. There's essentially us trying to pull 2 statements that have to be true out of this word problem. One is, I need a certain amount of stuff. The second is, that stuff has to contain. And so it's like, okay, let's maybe see how we can arrange this out a little bit. Maybe I want to now start playing with these symbols and make these a little bit nicer. So X plus Y equals 4, just about as simple as we can get. On this other one over here, the percentages, I think, is adding a little bit of clutter. I could maybe write this as 0.5X plus 0.1Y equals 0.2 times 4. Oh, I guess that'd just be 0.8. Maybe the decimals are bothering me. I could try to change the entire equation so that the decimals, maybe I scale this entire thing up so that I can get away from the decimals. That'd be multiplying everything by 10. That'd be 5x plus 1y equals 8. And that happens from just simply saying I'm multiplying everything on the right-hand side and the left-hand side by 10. Now, what is it that we're actually doing here? We're actually in the word problem, and if we were going to try to mirror this with physical objects, we would be trying to make 10 batches of this situation so that we could get away from so much percentages. But obviously, it's easier to do that on the paper by just simply saying timesing by 10 gets rid of that decimal feature, kind of moves everything over and scales it up. Well, what can we do from here? I've got 2 equations that I'm probably going to be playing off of each other. One equation here and another equation here. What can we do? Oh, well, isn't this 1y something that kind of looks like a common link over here? So I can do off to the side, I can say, let's maybe do equation 2, and we'll take away equation 1. That would be 5x plus 1y equals 8, and we're taking away x plus y. That's taking away x plus y equals 4. And if we take that entire thing away, I think we will be left with 4x is equal to 4, which means that x has to be equal to 1. Great. How do we figure out what y is? We could plug it into any of the things that we see above. Absolutely, we could plug it into this one here and say that x is equal to 1. That means y has to be equal to 3. So we could kind of say we'll use equation 1 again, and we'll say within equation 1, that is x equals 1, so we'll just say 1 plus y has to be equal to 3, or has to be equal to 4, so that means that y has to be equal to 3. And we can play with moving this entire thing around and using any of the statements that are true because they're all derived from something else that's true. It's a really, really powerful way of saying we can just play these things into each other over and over again. I've moved the other problem down because I want to actually use some space because there's a pattern that I'd like to explore with you. Now, we've been calling and kind of synonymously across the semester calling these linear equations, right? This is an original statement that is a linear equation because we're talking about having unknowns that are just to the first power. There's no square roots of the unknowns, and I have a certain amount of x's, a certain amount of y's. Just like over here, I have a certain amount of x's and a certain amount of y's. So we can have any amount. We can put numbers that are decimals or percentages or fractions or square roots in front of these unknowns, so long as we leave the x and the y pretty bare and plain. Now, why are these called linear equations? We should start to recognize that the reason why they're called linear equations is because they would graph as lines. So we have x plus y equals 4. This is actually a line in standard form, right? Standard form, as just to kind of recall, standard form is anything where it's ax plus by equals c. In other words, where you have all of your variables and the amount of those variables on one side. In this one up here, we actually have something else that's in standard form. This one, right, with the 50% and 10% solution, just because we changed its appearance doesn't mean we changed its meaning. That's another one that is in standard form. 5x plus 1y equals 8. Well, if they're linear equations, shouldn't we be able to graph them as lines? Let's take a look. I don't know how to graph this one off the top of my head, but I could make it into a format of something that I know how to graph, like slope-intercept form. Let's get the y value alone by subtracting x from both sides, subtracting the statement of x from both sides, and sure enough, that's going to get us negative x plus 4. Over on this other one, we would have y is equal to negative 5x plus 8, and I'm kind of curious, what's happening in this graph? Well, I know how to graph y equals negative x plus 4. Let's do 1, 2, 3, 4. That'd be this one right here. And then I could say, okay, well, what about in this? So I go up 4 and I go down 1 each time. That would be this graph right here. For the next one, I have negative 5x plus 8, so I need to go up to 8. 5, 6, 7, 8. And then from there, I would going 5 steps down every time I go 1 across. That'd be 1, 2, 3, 4, 5, and 1 across would be right here. And then 1, 2, 3, 4, 5, and 1 across would be next right here. So this equation is going to come out to be, let's see if I can draw this nice and straight, something right here. So as it turns out, they actually cross. They're two equations of lines that actually cross. And where is it that they cross? They cross at 1, 3. Well, isn't that interesting? After all, 1 and 3 were the answers that I had when I was solving this whole thing out using my equations. X equals 1 and y equals 3. So what's actually happening in this graph that causes everything here to look like it's got a parallel kind of situation happening? Well, what's actually happening is you're trying to look at where two statements are both true. Here, this original statement was saying something along the lines of, I am about to mix any amount of my first solution and any amount of my second solution so that I get 4 gallons at the end of that process. That works out just fine. This other one over here has a different statement. This one says I'm about to put some salt in from one thing and some salt in from the other thing so that I have a total amount of salt at the end. Okay. And by combining them together, what we're saying is that I want to not only have a certain amount of solution, but I want to have a certain amount of salt in that solution. And you say, okay, well, both of those paradigms are only the same thing when the lines cross right here at 1, 3. This is the thing that satisfies both of the situations. Isn't that kind of interesting? In fact, now that I'm kind of thinking about that, if y and x are the exact same thing, shouldn't we be able to come up with even another strategy? Like, let me try one more thing that I'm looking at. One more thing that I'm thinking of is, what about if in equation 1 I had x plus y equals 4, and in the second equation we had it again, we had 5x plus 1y equals 8, and I wanted to assume that this could be done, that I thought that there should be a y value out there that makes this entire statement true. Well then, what if I did something like this? What if I originally just said I was going to find out what that y value was in terms of the first equation, and I was going to find out how that worked if I put it into the second equation. After all, if y equals all of this stuff, then I should be able to replace y with all of that stuff. It's the same thing, it just looks differently. Well, what happens? 5x plus 1y, but instead of y, I'll write the meaning of this y. It's this one right here, equals 8. We could simplify this entire thing down. 5x minus x plus 4 equals 8, gets us 4x plus 4 equals 8, which gets us 4x equals 4, which gets us x equals 1. And if I put that into any of the true statements that I've had at the beginning, or from anywhere from the beginning, I could put it into this true statement. I could put it into this true statement. I could even put it into, well, probably not this true statement right here because there are no y's. It would work absolutely, but I just wouldn't learn anything from it. Oh, I could put it into this true statement right here. Any of these will get us the exact same thing. It'll get us that y has to equal 3. And lo and behold, we've got the exact same thing that we had in both the situations above. Y equals 3 and x equals 1. So I want us to take a moment and kind of broaden out from this idea of saying we have to solve these problems in a certain way to recognize that really what we're doing is just any model of logic that we want. We could say, if two statements are true, then I could continue to adjust one statement by taking away the other statement, or in some cases adding, or I guess scaling, or doing whatever we wanted. We could just kind of look at that as the picture rippling, like we did the popcorn and the soda example, or we could look at it as just two statements that I'm trying to figure out if they will both be satisfied. That's like when we're graphing it right here and trying to find out when is it actually that both things occur. Or we could even look at it as saying, well, if I assume both things occur and I plug one into the other, then I'm not talking about two unknowns anymore. I'm talking about one unknown, and I should be able to find out exactly where that one unknown is, and then just kind of look back in my story for what the other has to be also be true. These are three different strategies. One is called elimination. So the first one we looked at was called elimination. It's this idea of saying that I'm going to use different equations to subtract and manipulate the appearance so that I eventually get one thing alone that I can use to backfill up through all of my unknowns. The second one is this graphing solution. We're looking for where do these equations intersect, because wherever they intersect is going to be an x and a y value that's true for both statements. So we can absolutely just look at the picture, find out where the pictures tell us we're going to have this kind of overlap, and then that's going to be our graphing solution. And then you also have this one down here, which is called substitution. And substitution is this idea that says what you can do whenever you're trying to work with two different unknowns is just simply say, you know what, I don't want to talk about two different unknowns. I'm going to change one of them so that their appearance looks different, but their meaning stays the same. And that can be really, really strategic because it allows for us to talk about things that used to be two unknowns in terms of just one unknown. And that's going to help us get to solutions much more quickly. So let's take a look at how we would use each of these different solutions in a different problem below. So for this one here, I've chosen a specifically difficult problem so that we maybe feel a little bit of burden just trying to do this with pictures alone, and we start to move ourselves toward this idea of graphing or using equations or using substitution, and we'll try this in a few different ways. So during one night at the Jazz Festival, 2,100 tickets were sold. That seems like an important piece of information, so I'm going to write that down. So maybe I'll use tickets as being capital T, and I'll say that that's 2,100 tickets. Okay. Adult tickets sold for $12, and child tickets sold for $7. So maybe I'll do that. Okay, so that'll be adult tickets. I'll call A. I'll give it meaningful names. $7, and then, or sorry, $12, and then the children tickets were $7. So I'll call those C. So that's going to be $7. Okay. To better fine-tune their marketing strategy, the festival planners would like to know whether there are more adult or child tickets were sold. If the receipts totaled $22,100, okay, so maybe I'll call like the total receipts T, No, I actually already used T, so let's make sure we're giving it meaningful names. Maybe I'll talk about that as being the total amount of money. I'll use M, or I could talk about it as being the receipts, R. Maybe I'll use R. So I'll say R is equal to 22,100. Okay, and then how many of each ticket type were sold? So what am I trying to figure out from here? I'm trying to figure out the number of adult tickets. Okay, so I'll call that one adult tickets would be question mark. No, I've already used adults for A. What could we use? Let's call this one up here. I don't know. Let's maybe I want to connect these. Okay, here's my thoughts. Why don't I go back through and I'll relabel these, and I will call this one the price, but I'll put a little A here to remind me that it's the price for the adults. Okay, so this is just kind of one label. I've got P with a little a, we call it a subscript. It's going to help me keep in track of the fact that I'm looking for the number of adult tickets. This is the price for the adult tickets. And here I have the price for the children tickets, and that would be leaving up my variable to say, okay, I'll call this children tickets down here. One other thing I like to do, especially in problems like this that just have so much going on, is I like to go through this thing and then just kind of put in some more labels. So what do we have for the 2100? This is the number of tickets. On the next one, I like to say this is going to be the price for the adult tickets. This next here was the price for the child tickets. For this one down here, this was the amount of receipts. For the next one here, this is the number of adult tickets. And then this one over here would be the number of child tickets. Okay, so I try to take as much out of my head, put it down on the paper so that I can look at this later and not lose track of my meaning. Okay, I've got that there. That's wonderful. That's a lot of pieces of information. Now we need to step into the modeling idea. What could we do for our pictures? Is there a picture we could draw? Let's think. 2,100 tickets were sold. That sounds like a lot of tickets, like a stack of tickets. Maybe I'll draw that as a block. So I'll say this is going to be my picture for the total amount of tickets I sold. After all, I've got 2,100 right here. This is what 21 tickets looks like stacked on top of each other. That's all 2,100. What's inside of this 2,100 tickets? I guess some of it's going to be my adult and some of it's going to be my child. So I'll just kind of put something in here that says part of this is my adult, part of this is my child. Don't know how much is each. That seems fine. Okay, excellent. What's another picture I could draw? Well, I guess we made some money. I could draw a bag of money. So let's see if I could do that one. So we'll do this. We'll give it a few ruffles there and give it a nice little cinch with a couple of little ropes there. Okay, so this is going to be our total amount of money. How did I get money into the bag? Did I put $12 into the bag? No, I did $12 for every ticket. So, okay, so in here, I've got some of this that's not just the $12, the price of the adult tickets, but it's the number of 12s that I have in here. I have 12 and 12 and 12, etc. And then I have 7 and 7 and 7, etc. Okay, well, let's make that one maybe a little bit more clear. That's going to naturally lead me to maybe thinking of it in terms of an equation. I have $12 that I made every time I sold an adult ticket. So, okay, that's 12 for each adult ticket. What about in the next one? That would be $7 for each child ticket. And in total, that got us, what? $22,100. Okay, that worked out pretty well. I got one statement from there. And in fact, I think I could get another equation right here. This is saying A plus C had to be 2,100. Okay, very nice. So what can we do from this one? Strategies in mind? Let's maybe try the substitution idea. Right? Substitution means I need to eventually find something I can plug into the other. So let's do each of the strategies. Why not? We'll do strategy number 1. And then you can use these as references when you're solving your other problems in whatever way you'd like. The first one we'll try substitution. That would be, let's make it look a little bit cleaner. 12A plus 7C equals $22,100. Okay? And then we have equation 2, so that was equation 1. Let's call this equation 2. This is A plus C equals 2100. Okay, and in fact, maybe we'll get rid of the dollar signs here because I think that's just going to go and clutter things up eventually. We'll have 22,100. Which of these do I want to plug into the other? Well, I could think, if we want to think a little bit here before we just start running, if I wanted to get something like A equals over here to eventually plug into the other one, I'm going to have to do a lot of moving stuff away. And the same thing with the C. Could it be done? Sure, why not? But is that the easiest strategy, the most elegant? Maybe not. What about over here? Could we make this something like A equals? Yeah, we would just need to move the C over. So that'd be 2100 minus C, right? From subtracting the statement C equals C from both sides. Okay, well then, what's that going to give us? I think we'll use that as our basis, and we'll plug it into the other one. That would be 12A. Ooh, let's not use A. Let's replace it with something that has the same meaning, different appearance. 2100 minus C plus 7C equals 22,100. And then I think we could simplify up from there. That would be 12 times 2100. Oh, maybe I pull out my calculator from that one. So let's do 12 times 2100. Gets us 25,200. Minus 12C plus 7C equals 22,100. From there, we can simplify this out quite a bit. This would be 25,200 minus 5C equals 22,100. We could subtract from both sides. That would get us what? 3,100, negative 3,100 as equaling negative 5C. And if we divide both sides by negative 5, we would get, let's see, 3,100 divided by 5 is 620. Would be the number of child tickets. Great. What could we do from there? We could go and try to connect it into A in any way we want. Here's a way we could connect it to A. Ooh, but that one looks like that one might be a lot. Here's a way I could connect it to A. That looks much, much better. In fact, here's another way I could connect it to A, but maybe not as good as the second one that I found. So let's just plug it into the second one. We'll put it back over here, and that would be what? A equals 2100 minus 6200, in other words, or 620. In other words, out of the 2100 tickets that I sold, 620 of them had to go to the children. So how much do I have left over for the adults? Well, that would have to be what? 1480. 1480 were for the adults. And there we have it, a nice way of being able to solve this thing out using substitution. Now, could we do this with elimination? Absolutely. Let's take a look at the elimination one, and then I'll leave the graphing one for you. So what's a way that we could do this one with elimination? Well, let's start again as if we had done this from the very beginning. We had the statement of 12A plus 7C equals 22,100. And over here we have A plus C equals 2,100. Okay, how would we want to do this as elimination? Well, just like in the example with the popcorn and the sodas, I'd be trying to stack this up in such a way that I could subtract a good chunk away. But maybe I don't want to do this in a rippling effect. Maybe I want to try to simplify this up. After all, I see 7 C's right here that are kind of grabbing my attention as maybe the easiest thing to try to get rid of. But I only have 1 C over here. Well, let's take a moment. What was the meaning again? A plus C was 2,100. It's the number of tickets that I sold. And had I sold more, I would have just scaled everything up. I think that gives me an idea. Couldn't we just look at this as 7A plus 7C equals 7 times 2,100, which would just be 14,700? Like, that has to be a true statement. Had I sold 7 times more of everything, this would have been what we had. Well, now that gives me a great place to go over here and to say, why don't I just try to subtract this new statement that I made? I'll subtract the 7A plus 7C equals 14,700 from both sides and take a look at what we can get. Let's put that in the calculator. So in the calculator, we're going to have 22,100 minus 14,700 gets us 7,400. So we'll put that in down here, 7,400. And on the left-hand side, we have 5a. So let's do our division from there. 7,400 divided by 5a, or divided by 5, would be 1480. And that would be the number of adult tickets. Let's see, does it match? Yeah, it does. Take a look right here. There it is. 1480 is the same thing we got when we were working up here. 1480 and 1480. And from there, we have the exact same strategy of being able to use this 1480 somewhere else. We can put it into any of these true statements. Let's look back into some of the true statements we have as an option. I'm going to try to recognize that this one here looks pretty straightforward as being a way that I can connect A back to C. So let's put it in. That would be A is 1480. I can replace A with anything that's the same thing as A. It just looks different. Plus C has to be 2100. In other words, just like we had in our picture above, if I sold 2100 total tickets and this many went to the adults, how many went to the children? Whatever was left. 2100 minus 1480. So 2100 minus 1480 is going to get us the 620, and it's the exact same thing. Now, this one here is going to be definitely more challenging to do as a graph, but we absolutely could do it as a graph. We would just need to solve anything out for C and make that equal to Y, and X and make that equal to A. Like, we could do it, maybe not the easiest strategy to tackle with such big numbers here. So substitution and elimination really give us the power of being able to extend our intuition into even some of the most difficult problems, because all we're recognizing is that if I've labeled something and it means something else, then I can use those in whatever way suits me, because I'm not changing the meaning, I'm just changing my perspective.